So now we will talk about classification of random variables. First classification, we can understand that random variables can be categorized into three types. One are discrete random variable, continuous random variable, and mixed random variable, which have some properties from discrete and some from continuous. So for this classification, we have to understand what is the range of a random variable. And this classification usually depends on the range of a random variable. So we know random variable is a function from omega to r. So let Rx be the range of x. So what is the range? Range means if you collect all, see, not all numbers in real line will be mapped to one outcome in omega. So omega, this function takes outcomes from capital omega and maps to some number. If I collect all these numbers which are mapped to at least one omega, then I will get the range of x. Okay, so this is consistent with the range of function, which means that if a function is defined from a to b, then the set of all y says that y is fx equal to fx for one x or at least one x in a. Okay, so some members of B codomain will be left out. We will not include those. We will only include those elements which are mapped to at least one of the outcome, and that will make the range. And of course, you can understand this range is a subset of real line. It's a subset of a codomain. For any function, cardinality of its range should be less than or equal to cardinality of its domain. Okay, so why this is true? Because the function, if you recall, function maps one element of domain to one element in codomain, and only one element in codomain. It cannot map to one x to two values, right? So what it means that if x is if you take any x, fx would be only one value. It cannot be mapped to two values. It cannot be like fx is equal to also 1 and fx is also equal to 2. So this means the number of images. So if you take all outcomes in capital omega, and if you collect their images in codomain, the set of all those images, which is range, will have now elements which are less or equal to a number of elements in the domain. Okay, try to convince yourself about this, because you are mapping one element in codomain to only one element in one element in domain to only one element in codomain. Your maps will be less. And of course, you can map to x1 and x2 to a single number. So if you map all of them to a single number, range will only contain one value. But range can contain, and if you map each outcome to a different number, your range will have same number of elements as the number of elements in the domain. This will be a bijection map then. So, but there is no way you can have more number of elements in the range. So now, depending on the cardinality of capital omega, the cardinality of R can be finite, countable, or uncountable. Let us denote the cardinality of range of x by nx. So now we can see that we can take three cases. Suppose the cardinality of capital omega is finite. It means there are finite number of outcomes. Then from the previous discussion, we know the range should be finite only. Cardinality of range is less than the cardinality of your domain. So if omega is finite, then nx will also be finite. The example would be, take omega represent a flip of coin. So it will have two outcome ht. If you map h and t to separate numbers 1 and 2, then range would be 1 and 2, which is 2. If you map these two numbers to both the same number, like x of h is also 1 and xt is also 1, then the range will be 1. In both cases, it will be finite. Now suppose omega is countable. Let's see, omega is countable infinite. Then nx can be either finite or can be countable infinite also. So let us take this example. Omega is equal to natural number set. So it is represent an experiment where you pick one number, one natural number, any number. So if I define a random variable x1 such that x1 omega is equal to omega. So if you pick 1, the random variable value would be 1. If you pick 2, random variable will be 2, like this. So in that case, the range would be the complete natural number set. Okay, so in that case, the range is countable. Suppose I map this, I find another random variable x2, and which is defined as x2 omega is equal to 0 if omega is even and 1 if omega is odd. So if you pick 1, x2 would be 1. If you pick 2 or 4, x2 would be 0. So in that case, x2 only takes two values, 0 and 1. So its range has cardinality of 2, which is finite. Third would be when omega is uncountable. In that case, range can be finite, countable, or uncountable. Let us take an example here. Suppose omega is 0 to 1, and the experiment is to pick a real number between 0 to 1. So outcome will be one number. And let us define x1 as x1 omega is 0 if omega is between 0 to 0.5 and 1 if omega is greater than 0.5 and less than 1. So this means if you pick 0.6, x1 will become 1. If you pick 0.4, x1 will become 0. So in that case, x1 only takes two values, 0 and 1. So its range is 0, 0, 1, and the cardinality is 2, which is finite. If you take x2 omega equal to the seal of 1 upon omega. Well, seal means it is the if you take any number, seal is the largest integer. Sorry, the smallest integer bigger than this. So bigger than or equal to this. So in that case, if you pick here, so I am defining x2 omega is 1 upon omega c. So if you pick like 0.15, so you calculate 1 upon 0.15, which is 6 point something. So seal will be 7. So it will be mapped to 7. So you can understand that no matter what numbers we pick, you will get one integer as x2. And this will cover all natural numbers. You can take any if you take omega arbitrarily small, you get number as big as you want. So the range here will be natural number, which is countable infinite. And third, I can just simply take x3 omega is equal to omega. In that case, if you pick 0.1, my x3 will just display 0.1. So range will be the complete 0, 1 sample space. So in that case, my range would be uncountable. The range of random variable will be uncountable. First, see the first type of random variable, which is discrete random variable. So a random variable x is a discrete random variable if the range of this random variable is finite or countable with probability 1. So we have discussed what is the range of random variable in the last class. So you just collect all the values random variable can take. And what we want to say that if this range is finite or countable, then the random variable will be a discrete random variable. And in this calculation, we can ignore those values which random variable take with 0 probability. So now what can be the example of this? Let's see one which is indicator random variable. Let omega fp be a probability space, and then let us assume E is a subset of omega. So E is some event which is in sigma algebra F, then the indicator of this event is defined as is a random variable which is defined as x omega is 1 if the omega is in E and 0 if omega is in E complement. So it's a random variable which so it's a function of outcome. It just tells that a particular outcome is in event E or not. So if you perform this random experiment, if E has occurred, it means the random variable will take value 1, and if E has not occurred, then the random variable will take value 0. So you have to see it two ways. In mathematically, this is just a function. So if random is a function of outcomes. So if omega, which is the element of capital omega. So if you take omega as a member of E, then x omega is 1. And if omega is in E complement, is not in E, then x omega is 0. Okay. And then from using the interpretation of random variable, you can relate that this actually means if you perform this experiment, then if the outcome in E has occurred, or in other words, if event E has occurred, then the x will take value 1, or otherwise x value would be 0. So this is an indicator of event E because this random variable denotes whether the event E has occurred or not. So sometimes we also denote it in the shortcut saying that x omega is indicator that omega belongs to E. So this is a random variable. You can prove this simply. So let us first assign a probability measure. Suppose P is P and P complement 1 minus P, and these are possible because E is a element of sigma space. So probability measure can be defined. So this is a discrete probability space because x only takes two values, 0 and 1. So let us see if b is equal to minus infinity comma x, and if you take x and the value less than 0, then if you find the inverse map, then what are the outcomes which map to any number between minus infinity and some negative value? None of them, because a random variable either maps to 0 or 1 in this case. So there will not be any element which is mapped, will not be any omega which is mapped to minus infinity to a negative number like minus 1. So the inverse image would be empty, and phi belongs to F. Okay, and here we also can compute the probability of phi, which is 0. So this will tell that in this particular case, if B is this, then the probability law on B is equal to probability of the pre-image of B, which is phi, and it should be 0. Now let's take another case. Let's take B equal to minus 20 to 0. So now in this case, x is 0. So what is the pre-image of that? It will include all the outcomes which maps to 0 also. And what are the outcomes which map to 0? So all the outcomes in E complement map to 0, and no other element map to 0. So this means pre-image of B would be E complement, which is also in F, because E is in F, so E complement will be in F. Similarly, you can show that if x is more than 0 and less than 1, then minus infinity comma x, if you find its pre-image, it will only include E complement. It will not include E because E maps to 1. All elements in E maps to 1, which is not included in B. So this also belongs to F. Similarly, if you take minus infinity comma 1, then if you find the pre-image, it will include both 0 and 1. So it will include all omegas. So a pre-image is the complete sample space. And if x is more than 1, then also no matter what value of x, how large the value of x is, if x is more than 1, then this pre-image will include the complete sample space, which is also in F. So we have seen for any values of x, minus 20 comma x belongs to the pre-image of this belongs to F, so it's a random variable. Now we can also compute the probability law because we already know the pre-image. So when B is minus 20 comma 0, the pre-image will be probability of pre-image will be E complement. So probability law on B will be probability of E complement, which is 1 minus B. Similarly, we can calculate So if x, if it is 1, then it will be 1. More than 1, it will be 1. If it is between 0 to 1 or 0, then it will be 1 minus p. So we can nicely write it in terms of x, which is also the CDF. So CDF of x, which is the probability law of minus infinity comma x, is 0 if x is less than 0, 1 minus p if 0 is between x and 1 if x is more than or equal to 1. So if you plot it, it will look like this, that up to 0, this is 0. And at 0 and after that, it becomes 1 minus p. And at 1 and after that, it will become 1. So there are jumps on this CDF. Okay, and these jumps occurs at the point, the range values of x. Okay, you can see that whenever you include one element, one member of the range of x, then once you include that, you will immediately include some more elements in the pre-image, okay, which maps to this new number. So up to minus 20 comma x, there was no element in pre-image. Once you include 0, all elements which map to 0 are already included, will be included in this pre-image. Okay, and because of this inclusion, the probability inclusion in the B, this probability corresponding to this new element will be added. Okay, similarly, you can see up to x less than 1, the pre-image is E complement. Once you include 1 also in this set, then suddenly all the elements which maps to 1 are also included in E complement, and those are all E. So E is included along with E complement, so the complete set will become complete omega. And then you will see there is an increase in the probability of this set because E complement was 1 minus P, and the new added set E has a probability measure P. So once you add that, the probability will become 1 minus P plus P, which is 1. Okay, so this is what this tells you. This is a discrete random variable because if there are finite points and corresponding to each point, there is a mass you are adding to it. Okay, there is some constant value you are adding to the probability of pre-image of minus infinity comma x. Okay, so what you find here in this case, there are two jumps. So this can also be understood that we can see that whatever we are adding here, see this is minus 20 comma x. Okay, minus 20 comma 1, but 1 is open, so we are not including 1. And once we include 1, suddenly we have a 1 minus p added, right? So you can understand we are adding 1 to minus, sorry, we are, sorry, in this case it's 0. So minus infinity comma 0 open, we are adding a singleton element 0 to it. And once we add it, we get minus infinity comma 0 closed interval. And that probability is 1 minus p. Okay, and minus infinity comma 0 open has 0 probability. So this means the singleton set you are adding has a probability of 1 minus p. Similarly here, the set minus infinity comma 1 open has a probability of 1 minus p. And the set minus infinity comma p close, sorry, minus infinity comma 1 close has a probability 1. Okay, so this means the probability of singleton set 1 is p here, 1 minus p. So this you can understand from this here also. So what is the pre-image of 0, singleton set 0? The pre-image of singleton set 0 is all omega which maps to this, which maps to 0, this element, and that is equal to E complement. So probability probability law of this set 0 is equal to probability of pre-image of 0, which is probability of E complement, which is 1 minus p. Similarly, pre-image of singleton element 1 is all elements which map to 1, and that is just E. So probability of this set is probability of E, which is P. And if you take any other singleton set, probability of X would be probability that all element which maps to X. And because their outcomes only map to 0 and 1, if you ask how many elements map to another element X, the answer would be empty. No elements map to any other value. So we can see if you take the probability of this, you will get just 0. So probability of the singleton set X is 0 for all X which is not 0 or 1, and it is P if that X is 1 and 1 minus P if X is 0. Okay, so if you plot this function, you will find that this singleton set probability function, which is a so this is a function of x, which denotes the probability of the singleton set containing only x. So if you plot this function, you will find it has 0 it is 1 minus p, 1 it is p, and rest value it is 0. Okay, so we can define this as a new function p, which would denote as p capital X x is equal to probability of the pre-image of the singleton set. Okay, or the probability law of the singleton set x. Okay, so there is a typo here. It should be probability of the pre-image of x, or the probability law of singleton set x. So this new function, which is a function of x, and of course depends on random variable x. This is known as the probability mass function. Why? Because this shows the probability of a mass at 0. Okay, so because once you include 0, with that 0 represents, this singleton set 0 represents a set E complement. So once you include that, you are including the complete probability to this new set. Okay, and probability measure is a measure, right? And measure is also a mass is also a measure. So sometimes people call it probability mass because it's like a measure. Okay, so that is why this is called probability mass function, or sometimes PMF of x. And this is a property of discrete random variable that you get this PMF. Okay, so now we can extend this example to other cases also. Suppose the range of R is countable. Okay, then of course, if it's countable, we can order the elements into x1, x2, x3 in the increasing order. Okay, or even in any order, you can have x1, x2, x3. Okay, so this means that for every I, probability of singleton set xi is the probability of all outcomes which map to xi. Okay, and because this, I assume that the range, I'm including all elements which have some non-zero probability of occurring. So the probability that x omega takes xi, that is some value, let's call it pi. Okay, so for every I, you just take xi from the ordering you got, and this order can be anything, but there is an order exists because of R is countable. So because of that, you can say the probability of the probability law of the single center containing only xi is the probability of all outcome which map to xi, and let's take that value is some value pi. Okay, and of course it's a random variable, so this pre-image will be in sigma algebra, so probability is exists. And what we want is, if I add all those singleton set, then I should be able to get all values of what x can take, and the probability of that should be 1, because the pre-image of that set where x can take any of these values is complete sample space. So what we want here is sum of all pi should be 1. Okay, and for CDF, if you plot the CDF, you will find out that for any xi, if you take a set from minus infinity to xi without including xi, so basically an open set from minus infinity comma x, you get some probability, and once you add xi to it to get the closed set minus infinity comma xi, there will be a sudden jump from the sudden jump, which will be of the jump amount will be equal to the probability of this singleton set xi. So once you include this xi once more, you get a chunk of event also being added to your pre-image, and because of that, the probability of pre-image will increase. So for each xi, you will see there is a jump which is equivalent to pi. Okay, so if you order them also in the increasing order, you will find this would be the CDF. Once support takes 4 values, then at 1 you will get x1, and there will be, once you include x1, you will take a jump of p1, which is equal to the probability of things singleton set containing only x1. Similarly, at x2 you will again one more jump like this, and eventually, if you cover all jumps, then you should reach 1. Okay, because the total mass at all those points should be equal to 1 because of the probability axiom. Okay, and of course it should start from 0. So when it is minus infinity, the CDF value is 0. Okay, so this is what this discrete random variable term is coming up. If you plot the CDF, it will look like a discrete CDF, right? It's discontinuous, left discontinuous. Okay, so CDF is always continuous on the right side, but from the left side it is discontinuous. So that is why this is a discrete CDF, and here therefore this random variable who have such discrete CDF are called discrete random variable. Okay, and the way you can show that this is discrete CDF as a random variable, discrete random variable, by just knowing if the range is countable or finite. So now we come up to another point. Can two different random variables can have the same distribution? Okay. So this I will tell from the perspective of discrete random variable, but this discussion is also true for the continuous random variable. So let's see. I gave another example where the CDF, I have calculated an indicator random variable uh, of a event E, and I computed CDF is of this form. Okay. Now let us consider that there is another set E prime. It is different than E. It's another set. It's an event which also belongs to sigma algebra, and such that the probability of E dash is also P. Okay. So in the same sample space, it is possible to find two different events with the same probability. Okay. Like if you take head and flipping of a coin, which get head and tail. So probability of the event that head has occurred is also half, and probability of the tail has occurred is also half. So there are two events. E would be head has occurred, and E dash will be tail has occurred. Both have same probability, but they are not the same events. So E dash is another event which is not equal to E, but it belongs to sigma algebra, and the probability of this set is P, also P. Then we can define another indicator variable y omega, which is the indicator of this E dash. So y omega is 1 if omega belongs to E dash, and 0 if omega does not belong to E dash. Okay, and so this y omega is nothing but is an indicator of that event E dash has occurred. So whenever you do the experiment and E dash has occurred, any outcome in E dash has occurred, then the value of y will be 1. Okay, so if you calculate the CDF of y, you will find out that the CDF of y is exactly equal to this what we get for the CDF of x. Okay, because here also when you take a probability of corresponding to 0 would be probability of E complement, which is also 1 minus, sorry, probability of E dash complement, which is also 1 minus P. Probability corresponding to 1 is probability of E dash, which is also P. So CDF is equal. But if I ask, is x is equal to y, right? So again, x and y are both functions. So before we can say that they are same or not, we have to understand what is equality of function means. Okay, so how do we compare two functions? Right, suppose I give you a sin x and cos x and ask you, are they equal? So how do we find out? So generally the answer is we say the two functions are equal when they are equal for every value. Okay, because they are not just one value, they have a function which maps from one value to another value. So first we have to make sure that they are defined on the same domain. Okay, so that for any value you take, you can calculate the value of both functions. And once you are able to do that, you make sure that they are equal for every value. Okay, so x and y would be equal if x omega is y omega for every value of omega in the sample space. Okay, so x omega here is 1 0 for this, and y omega is 1 for omega belongs to E dash. And if you take any omega 1 which belongs to E but does not belongs to E complement, then for that omega 1, x omega 1 would be 1, but y omega 1 would be G. So you have found one omega 1 value for which x omega and y omega is different. So this means these two random variables are not equal because they have at least one disparity between the two. Okay, even without this thing, we have seen that they can have the same distribution. Now, let us move to continuous random variables. So, let us first consider the case when range of x is uncountable. So, in the previous case, when we were talking about discrete random variables, we were talking about we took the range of x as countable or finite. Here we have to consider the case where range of x is uncountable. So this we know CDF that each jump in distribution function corresponds to the probability of that singleton element. Now there are uncountable number of such singleton elements because we have taken the range as uncountable. So if you try to construct the singleton sets, they will be in uncountable number. We cannot have infinite jumps in distribution functions for each of these singleton, right? So if you have a jump for each of this singleton element, then there will be uncountable number of jumps. And even if you assign a small epsilon to each singleton, the summation will be infinity. But the summation can be 1 because if you add all the jumps, it should be the total probability of sample space, which is 1. So it is not possible to assign non-zero jumps to each of these singleton elements. So of course, not all singleton elements cannot have actually non-zero probability. Some of them you can take some of the singleton elements and can assign non-zero probability to them, but you cannot assign to all of them. And actually, you can say that you can assign to finite number of singleton elements or even countable number of singleton elements some non-zero probability, but there are uncountable number of singleton elements. So if you remove this countable number of singleton elements where you can assign non-zero probability, the rest are still a lot more than countable number of elements. So we can say that most of the singleton elements will have zero probability. Okay, so let us consider first the case when all of the singleton elements have zero probability. Okay, and then where some of them has non-zero and some have zero probability, that we will consider later. That will correspond to the mixed kind of random variables. So let us consider first that for all x, the probability law of singleton set is 0. It means if you take the pre-image of the singleton set, the probability corresponding to that will be 0. So the value that random variable takes, this value x, is 0. So now we know that probability of a singleton set is nothing but the CDF of x minus CDF of x minus, which is the left-hand side limit of the CDF. Okay, this we have proved in one of the previous lecture that for any singleton set x, if you take the difference of the CDF value at x and the left-hand side limit of the CDF, you will get the difference of the probability. This difference will be the probability of the singleton set. Okay, and discrete case we also see that this is not equal to 0 and that is the value of the jump at x. But in this case, since the jumps are 0, we will assign all of them are 0. So this means there will be no jump and the left hand side limit of CDF is also equal to the value at x, and right hand side is already continuous from right hand side. So what we can say that CDF is continuous from left and both sides. So it is a continuous at every x. Okay. So in other words, this also means that if you add x, a singleton set, which is a set of 0 length, to minus infinity comma x open set, it does not add any probability to this set. Okay. So when you add it, you will get minus infinity comma x closed set. Okay. But since the probability of this and the closed set is same because of this continuity, this means adding a singleton set x does not add any probability. Okay, and then you can also prove that if you add a countable number of singleton sets also, it will not add any probability. Okay, so a set of zero length, if you add it, this does not add any probability. Okay, what does zero length actually means? Because we are taking one dimensional random variable, so we talked about the zero length. If we had talked about other dimensions, 2 dimension, 3 dimension, then you take area or the volume. So in general, you can say Lebesgue measure. So a set of zero Lebesgue measure, if we add it, it does not add any probability. So this is how we get to the definition of continuous random variable. A random variable X is continuous random variable if for any Borel set B with Lebesgue measure 0, the probability probability law of that set is 0. Okay, so if you take any Borel set which has 0 Lebesgue measure, the probability of this set should be 0. Then this random variable would be called continuous random variable. Okay, uh, and what are these sets which have 0 measure? Of course, the singleton sets have 0 measure. Sets with countable number of elements also have 0 measure. Okay, so you have to prove that a random variable is continuous. You have to prove that the probability law of any Borel set of 0 measure, 0 Lebesgue measure is 0. Okay, so in general, this is continuous with respect to the Lebesgue measure. So CDF is continuous with respect to the Lebesgue measure, or the probability law is continuous with the respect to the Lebesgue measure. Okay, the CDF only includes like sets of the form minus infinity comma x. So probability law of those sets, but probability law includes any types of sets. So here the Borel set can be anything of 0 measure, 0 Lebesgue measure, and you have to show that continuous random variable for continuous random variable, the probability law of this set is 0. Okay, so not just one set, for all possible sets. So proving continuous random variable, you don't just take one Borel set and prove that this is a probability law of 0, but you have to show that for any Borel set we can take with 0 Lebesgue measure, the probability law should be 0. Okay, so let's take one example case. Let's take a person, consider a random experiment where a person arrives between 2 p.m. and 3 p.m. So his exact arrival time is the outcome. So outcome omega is a real value between 0 to 1, and it denotes the hour it arrives. Okay, so the sample space is 0, 1. It can take any real value between 0 to 1, and this denotes the fraction of hour he arrives. So if omega is 0.5, it means it arrives in the half hour, which means it arrives in the after 30 minutes. If it is 0.1, it means has arrived in 6 minutes. And let's assume the probability measure is uniform. So once we know the probability measure is uniform, then we talk about the random variable x. Okay, so see, the sample space is uncountable. Okay, but you can have and the probability measure is, that's why we have taken a probability measure uniform, which is Lebesgue measure. But notice that even on uncountable set sample space, you can have discrete random variable. Okay, so for example, you can divide the uncountable set into two parts, A1 and A2, and you can make an indicator random variable of A1. Then the random variable will only take value 1 and 0. So this will be a discrete random variable. Okay, so continuity doesn't have, it doesn't mean that if the countable, if the sample space is uncountable and the probability law probability measure is uniform, then it will be a continuous random variable. No. So probability measure can be uniform, but then what random variable you can take and what will be the probability law, on that the continuity of random variable is dependent on. So you can have two random variables, one on the same sample space and the same probability measure. One can be discrete and one can be continuous. So you need to know exactly the random variable before saying whether it's a continuous random variable or not. So let us say, consider a random variable x, which denotes the time in minutes passed before the person has arrived. So you know x is defined in a way that x omega for any omega is equal to 60 omega. So this means if omega is 0.5, the value of x would be 60 into 0.5, which is 30. So 30 minutes has been passed. So this is a function from 0, 1 to 0, 60. So we want to understand whether this is a continuous random variable or not. Okay, so let us compute first the pre-image under this random variable. So pre-image of minus infinity comma x is equal to a set of all outcomes such that x omega belongs to minus infinity comma x. Okay, and x omega is nothing but 60 omega. So it is set of all omega such that 60 omega belongs to minus infinity comma x. So you can say this is all a set of all omega such that omega belongs to minus infinity comma x by 60. Okay, so because now omega can only be between 0 to 1, so we know that omega can not take value less than 0. So this condition is equivalent to just saying that pre-image is equal to made of all omega such that omega is between 0 and x by 60. Okay, and of course it is also less than 1. So if x by 60 is more than, because x here can take any value up to infinity. So x by 60, if it is more than 1, then also those omega, because omega has to be a part of sample space also. So omega would be between 0 to 1 only if x by 60 x is more than 1, which means if x is more than 60. So this is what we know, that x inverse is equal to this, and if x is more than 60, so let's assume 75, then pre-image would be says that omega belongs to omega to 0 to 1.25, and because they omega can only be between 0 to 1, so all values from 1 to 1.25 does not mean anything. So this is nothing but the complete omega, because the complete omega belongs to this set. So in that case, the CDF fxx, which is the probability of minus infinity comma x for this value, would be just equal to 1. And when x is less than 0 also, then this will be probability law of minus infinity comma x, because s does not contain 0 or any number after 0, so there will not be any omega which maps to this. Okay, omega maps to a positive number only. So omega cannot map to a set which only has negative numbers. So probability would be 0. And between 0 to x by 60, the probability that probability of pre-image would be probability that of all omega says that omega is between x by 0 and x by 60, and the probability of this set is, because we have a uniform measure, this will be equal to x probability of 0 comma x by 60 is x by 60 minus 0. Remember, in uniform measure, probability of a comma b is b minus a. So probability of this is x by 60. So totally we can say the CDF will be given as it is 0 if x is less than or equal to 0, x by 60 if x is between 0 and 60, and if x is more than 60, it is 1. So once you plot it, you will get this like this CDF. And you can observe that this is a continuous random variable because there are no jumps in it. Now, okay, so it's also easy to prove this. This is continuous, right? You can take any small element and then you can know if the length is 0, then the right, you can take x and x plus epsilon a set, and you can say as epsilon goes to 0, the measure of set x comma x plus epsilon also goes to 0. So that is how you can prove continuity in one dimension. So let's take another random variable y that denotes the time left after the person has arrived. Okay, so if a person arrives at 40 minutes, the time left is 20 minutes. So y would be 20. So y would be defined as 61 minus omega. Okay, so this is just 60 minus x. Now, if you plot the, try to calculate the distribution of this, and you will find the CDF of x is given by this, which is exactly equal to CDF of x. So here also we can see there are two random variables which have the exact same CDF, but that does not mean the random variables are same. For every value, if you arrive in 20 minutes, x will be 20, but y will be 40. So the values of x and y, they are different, and in fact, They can be only same at only one value when a person arrives at 30 minutes. So now we will talk about the probability density function of a continuous random variable. So first we will talk about what is the density of a measure. Recall that measure denotes the size function, right? So if you have a set X and then I want to assign a measure on this, means if I take a small subset of this, I want to know what is the size of this. So it's like you have a big line and then you take any line segment on that and want to ask what is the size of it. So the way you can measure the size is by computing the length of that line. Similarly, if you have a big ground, you can just take and ask, I want to assign a measure on it. It means you can just take any two-dimensional region and then you want to ask what is the size of it, which can be done by knowing the area of it. Okay, but that is not just a single measure. Measure extends this definition. Someone can say that if you have a big ground, if I take any reason, I want to know how much grass is in it. So the area, it can be a bigger area in the perspective of its length cross width. So you can take a region which has a bigger area, but it may not have any grass. So it will be a zero measure. And a small area which has some grass, it will be has a non-zero measure. So a bigger set, which bigger means a set which looks bigger in area can have a small measure. Okay, according to new definition. So this measure can be anything. We can take the amount of a particular type of soil or the amount of water in the soil, right? So anything which can be assigned as a measure. Of course, we need to satisfy all property of measure that if you take two sets, if you add them together, the union will have the measure as a sum of the individual measures, right? And you know that for grass, it should be true because if you take two regions disjoint and if you add them together, the grass just adds up. So these are different types of measures. Uh, so in any case, they include size function. And then we always talk about, in this case, what is the density, right? So density in simple form would be size divided by the volume. Okay, so if you talk about the grass measure, then you would ask what is the density of this grass. So you take any region, you calculate how much grass is in on it, and then you divide by the area. That will give you the amount of grass per unit area. Okay. Similarly, if you take a stick and you want to assign a measure on it, and you say that the mass is a measure here. So you take a part of the stick, like a small segment of the stick, and then say the mass of this segment is the measure of this segment. So that's a valid measure because mass also adds up in the fashion of measures. Then you can say what is the density of that. Okay, so the particular density where you just divide size by the volume. Okay, so this size means generally the length or the area. So if you divide size by volume, which we'll call it the volumetric mass density. Okay, so you can take a stick and you compute the mass and divide by its length. That will be its density, and that will be called the volumetric mass density. So yeah, here size means the mass. Okay, but mass can be general. So that's why there's a lot of terms you will find which has mass in it, but mass is a measure. So sometimes people find the analog from mass, like density. Is generally we have seen density in terms of mass per unit area. That there's a stick. What is the density of it? The mass divided by the area or the length of that set, right? But mass can be replaced by any measure. Still, we use the same term density here also when we have another type of measure also. So let's take a one-dimensional case. Take a metal rod of length L and the mass is m. Okay, and just note that mass is also measure. So whatever discussion I'm making can be thought from the perspective of measure also. Then the density will be m by L. Okay, this will be unit will be kilogram per meter. And this is true when the rod is uniform. So when rod is, yes, when rod is uniform, you can just divide mass by length. What if rod is not uniformly made? Then you know that density will not be uniform. Some places, same length segment can have more mass, and other places it can have smaller mass. So the way density is defined is that suppose the density of at x is rho x, then the mass is given by integrating this density over the space. Okay, so this means you divide the length, the stick into small intervals of dx size. Okay, and since the density is rho x, the mass of that small segment of length dx would be rho x into dx. Okay, we assume the density is constant in that small segment of length dx because dx is very small. So the density is mass per length. So mass would be given by density into length. Length is dx, density is rho x. So mass dm would be equal to rho x into dx. And if I add all this thing, we get the density of the total stick. Similarly, this is not just true for the whole stick, this is also true for any small segment. So if you take a segment from A to B of the road of this rod, then its mass, which is this one, the mass would be equal to the integration of this rho x in this interval A comma B. Okay, and if your A comma B is very small, like suppose B is equal to A plus epsilon and epsilon is very small, then you can observe that this is the integration of rho x dx from A to A plus epsilon, and because dx is very small, the rho x can be taken as constant is equal to rho A or rho B, so that will be given by rho A into epsilon. So this integration can be replaced by rho A into epsilon for small segments. Okay, so for small segment, this is true that density is equal. So here density rho is equal to m by epsilon. So for small intervals, this will be true. But if you talk about long intervals and density is not uniform, you have to take an integration of the density. And this is true for any kind of any dimension, even 2D and 3D. This the length is changed to area and volume. So this was true for mass, but the same discussion you can apply for any measure because measures are a measures the size of a set. In some case, it measures the mass of that set. So let rho is a measure on B. Okay, this B is a Borel algebra. Then, so I'm talking only on the continuous case. Okay, so these are on the sets which are uncountable. So let B be a Borel set, which is an element in Borel algebra. And so lambda B would be the size of the set, the measure of that set. And then I'm still talking about one dimension. So this is Borel algebra on one dimension. So let B is a small Borel set from x to x plus e. Then lambda x comma x plus e would be the size of the set. And suppose this lambda, small lambda x is the density of the measure. Then we know that the measure of the set can be computed by integrating the density with length. Okay, and if it's a small interval, then this can be obtained just by multiplying the density with the length. So in this case, the measure of this small set x to x plus e should be equal to x plus epsilon should be equal to lambda x density multiplied by the length of the set, and the length of the set is epsilon. So this should be equal to lambda x into epsilon, and this is true for every x, and epsilon should be very small. And in any case, if you take a bigger set like from x a to b, then of course you have to add the measure of all those sets, and that is from because the measure, so you can add this joint sets mass together. So once you add it, you get the total size of the complete set. So size of a comma b would be equal to the size of these small sets. And in continuity, it will become integration of lambda x dx from a to b. So this is the definition of density. We say a measure capital lambda admits density small lambda if for every set A comma B, the measure of that set is equal to integration of density with respect to dx. Okay, if you can find such function says that you can compute the measure of any set A comma B by computing this integration, then this lambda small lambda x would be the density of the capital lambda measure. And why generally we require density? See, lambda is capital lambda measure is is a little bit complicated object, because to uniquely define it, you need to define it for every possible set. Okay, so if you want to define measure on B, you have to define it for every possible set on a set of Borel algebra, which are many. While a density is a function, you only have to define for every values of x. So you can write a nice function. But for a measure, you have to take every possible set which is possible, and then you have to define measure on it. So this density is a little bit easy to deal with, and they are unique in the sense that if you know the density, you can compute measure, and if you know the measure, you can compute a density. They cannot be two measure with the same density. They cannot be two density with the same measure. Okay, so okay, so this can be also applied for general D dimension. A measure capital lambda admit density lambda if for every Borel set A, lambda of that set is equal to lambda dx on this set A. Okay, now dx and lambda x are in D dimension. So dx is not just length, dx denotes the volume of a small region around x. Okay, so how this is important for probability? Again, remember probability is also a measure. Px you have defined is also a measure. So of course it has a special property. It can be between 0 to 1 only, but it's a measure. So we can define a density to it. So we can say that here Pxa is the probability of set A, which is like a size of this set A. Hence Px admits a density fx if the probability law of this set A is equal to, can be computed by integration of fx dx over set A, and this is true for every Borel set A. Then this density has a particular name because it is a density of probability measure. We call this as probability density function or PDF. Okay, so in short, we can also say that Pxab is the probability of set AB. Then Pxab would be equal to, which is equal to probability that x belongs to this set AB is equal to integration of this density from A to B. Okay, so if I tell you the PDF, you can compute the probability measure of any set AB. Okay, and it's an easy notation because you only have to give one function. You can write a nice mathematical form that this is my PDF, and then I will suddenly immediately know the probability measure of every possible Borel set by just doing this computation. Okay, now you can also understand that if A is very small, A to A plus epsilon, then the probability of that set. Okay, so probability law of that set A comma A plus epsilon means probability that x omega belongs to that set. Okay, which also remember this means that probability of all omega which maps to a value between A plus A plus epsilon. Okay, so if those outcome happens, A would be between A and A plus epsilon. I want to know the probability of that. Okay, so in shorthand, it is known as probability that x takes value between A and A plus epsilon. That will be just equal to fxa into dA. Okay, or if it is epsilon, then it will be fxa into epsilon. We don't have to do integration here because it's a small set, and we can assume fxa is constant in that. But if you take a bigger set, then of course you have to do integration. This is only for infinitesimal sets. Now also you can take minus infinity comma x, and because it is true for every Borel set, so this is also a Borel set. So you can say the CDF, which is the probability law of minus infinity comma x, should be equal to the integration of density with respect to dy from -70 comma x. Okay, so sometimes people do not talk about the complete probability law. They just take the CDF and calculate this. And we have proved in the past that CDF uniquely characterizes the probability law. If you know CDF, you can compute the probability law of any Borel set. So this is also a sufficient condition. You can show that if fx is such that a small fx is such that CDF for every possible x can be written in this following expression, then fx admits a density function which is given by this. Okay, and of course you can compute this. You can take the derivative from both sides. Dfx dx is equal to, and if you apply then you will find out that this PDF is nothing but the differentiation of f with respect to dx. And if it is a higher dimensional, then also this is true. You have to just do the higher dimensional differentiation. Okay, so from this we can get different formulas. We can say if PDF exists, then the following is true: probability that x belongs to B. The probability law of P is equal to density integration over B. Probability that x belongs to A comma B is integration of PDF from A to B. Probability that x belongs to A plus DA is integration from A to A plus DA. And because it is can be assumed to be constant because it's small interval, this will be just fxa into d. Okay, so if you apply this to the example we have taken, where x we have considered a waiting period where a person arrives between 2 to 3 p.m. and the random variable was 60 omega. For that case, we have computed this CDF. And then if you differentiate it, you will get, you can see that for x less than 0, fx is 0, so the differentiation is also 0. After 1, it is, after x greater than 60, it is 1, difference is constant, differentiation is also 0. And between 0 to x, 60 is x by 60, the differentiation will be 1 by 60. So if you plot it, you will find out that it has 0 outside 0 comma 60 interval, and between 0 to comma 60 interval it has a constant 1 by 60 density. Okay, so it has a uniform density in this interval from 0 to 60, and rest places it has a 0 density. Okay, and then you can try to integrate it, and you will find that you can take any Borel set, and that will be given by integration of this CDF. One thing to notice that because fx is constant in this interval, the integration would be just length of the interval multiplied by the height, because it will be in rectangular format. Okay, so any set you take from a comma b in the between, that will be just 1 by 60 into b minus. Okay, and that you can prove that it's also the probability measure here. So we have seen that what is the CDF of a random variable. So regardless of whether it's a discrete random variable or continuous random variable, the CDF exists. However, the form can be different. For continuous random variable, the CDF is continuous. It increases continuously, and then there is a discrete random variable for which the CDF is in the form of staircase. So there are some jumps at some particular points. Then we also see that the CDF can be sometimes complex because you have to specify. This can be, you have to specify for every value of x, and sometimes there is much more interesting parameter can also be computed, which is known as density. So what is density? Density kind of gives that how the probability is accumulating as we move around the range of random variables values. So let us see. So if we take a small area dx, the probability of this area that the random variable takes value in this area is fx into dx, where fx, the small fx is your density. And then this means that if you take an area A and suppose its probability is P1, then if you include this additional area of region of area dx, then the probability will increase by fx into dx. So the new probability would be original probability P1 plus fx into dx. So this density kind of shows that as you include more and more area in the interesting set, how does the probability increase? So this is the rate of increase of CDF or rate of increase of probability measure. So if you include a small area dx and the probability increases by p, then the rate will be p by dx. That is the density which is given to you. Now, for the discrete random variable, CDF does not increase continuously, but it has few jumps. So you can, that's why we don't define this density. We directly talk about the probability mass function, which denotes that the mass which can be accumulated by if you include those specific points. Now it's still possible. So CDF exists for both type of random variables. Although PDF is generally, when we say PDF, it is for constants random variable, and PMF for discrete random variable. However, to create some uniformity, it is also possible to define PDF for discrete random variables in a consistent way. Okay, so we can see that the if you have a discrete type staircase type function, CDF function, and the density is a kind of derivative of this because it shows the rate at which the CDF is increasing. So the derivative of a staircase function would be nothing but the set of impulses. So if a discrete random variable x takes value xi with probabilities pi's, and this can be countable number of values or finite values, then its PDF can be written as summation over all values pi delta x minus xi. So this is nothing but to say that it's a sum of different impulses at xi, where xi denotes the values this discrete random variable takes. So here, just to clarify, delta x minus a is an impulse at a. So it's a function of x and it's an impulse at a. And if you recall the definition of impulse, if you integrate impulse in any interval which includes a, then the value would be 1. And if the set does not include a, then the value is 0. So this just means that if the set you are interested in include xi, then you would have an additional probability of pi. So CDF of a discrete random variable is in the form of staircase. Each jump in CDF corresponds to a non-zero probability at that point. So the PDF of discrete random variable consists of impulses, and the value of any impulse at a location xi is the same as the value of jump at xi. So basically, if you integrate this PDF over any set B, and if that B include xi, then you will have the integration value equal to pi, because the value of impulse at xi is p. So we can also formally see this relation. So let's take a set, Borel set B. So probability law of B, which is also defined as the probability that x omega takes value in B, should be given by the integration of density over this set B. Okay. So recall that this is the definition of density, that we should be able to compute the probability law of any set by integrating the density over that set. So if the fx is actually a density, then they should satisfy this condition. Now let us see the density we have defined there, whether this makes sense or not. So density fx was defined as the summation over all i's, all possible values x can take, delta y minus xi yi. Okay, so I've used a y variable here. It's just a local variable, doesn't mean you can use x or y, any variable here. So now this integration and summation can switch the order. So summation will be outside pi, and then integration of bi delta y minus xi dy. So now if you look at this integration, delta y minus xi dy over set B, this is an integration of impulse over set B. And you know that this will be 1 if the interval B includes xi. Okay, so if any point y takes value xi in B, then this will be then this will be 1. Otherwise, if uh, b does not include xi, then the value would be 0. So this means this can be written as equivalently as the indicator xi comma b. So this is the indicator, which means if the argument is 2, then it takes value 1, otherwise 0. So if xi is in b, this will be 1, otherwise it will be 0. So this I can replace by this. So this becomes summation about pi 1 xi comma b. So it means probability law of any set b, it just summation of all pi's of all those values which are included in B. Okay, and that is what the probability law of a discrete random variable is. You just take, if I want to know what is the probability x takes a value in B, I just see how many values are included in B, and I add the probabilities corresponding to those values, and this is how you get the probability law of set B. So at many places you will see that there is an x defined as a random variable and the CDF is given. But it doesn't explicitly talk about what is the probability space omega at p. And then they ask different questions that what is the probability x is less than this. So why is it like this? Because we already know that we do need probability space always. Otherwise, this random variable, there's no sense to define this random variable. Random variable is a map from some sample space. So why do we see these cases where we do not explicitly mention the probability space and then just talk about the CDF of? So can we always define a probability space for the given CDF? If we can, then probably we can just ignore the discussion on the probability space. Okay, so this means that if x is a random variable and the CDF is given fx, then if there is a guarantee that the probability space can always be defined in a way that does not change any calculation with x, then we are fine. We may not need to talk about this probability space all the time, unless it's required. So the question is, let us suppose there exists a function fx that satisfies all the properties of a CDF. Then does there exist a probability space in which we can define the random variable x, which has the same CDF as fx? If we can, then we just assume that this can be one probability space where which is consistent, which has a random variable x, which is consistent with the definition given to us. So now let us say how we can construct this probability space. If we can, then probably this will answer our question. So one example which we take is, let's take sample space as real line, sigma algebra as Borel set on R, and a probability measure which is given as the probability measure of any interval from -infinity to x for any x is defined as fx. Okay, so this is the probability measure we are taking, that if I take any set -20 comma x, the probability measure of this set is fx. Okay, and fx is already given to you. And then we can always prove that this is a valid probability measure because fx is satisfying all properties of CDF. So it's increasing. So from that you can prove that if you probability measure always increases as you increase x, then you can always prove the additivity property and those also properties. So now define a random variable x omega is equal to omega, and our claim is the x, this x CDF is fx. So how do we show that? Let's take b equal to -infinity comma x. Then the CDF of x, fxx, is defined as probability that this x omega is less than x. Okay, or x omega takes value in this set b. Now, because x omega is omega, so this is same as saying that this is set probability of the set of all omega says that omega is less than x. Okay, or omega belongs to b. So what is the probability of, so this set omega belongs to b is nothing but the b itself. So what is the probability of b? The probability of -infinity comma x is by definition is equal to fx. So you can prove that for any x, the CDF of x is equal to fx. So this implies that if a function fx satisfies all the properties of CDF, and this condition necessary to make sure that this P we have taken is a valid probability measure. So if a function fx satisfies all the properties of CDF, we can always construct a probability space and define a random variable which has the same CDF. So this gives a justification that why sometimes we don't have to explicitly say about probability measure, because we can always construct one probability measure, and there may be calculation which does not actually depend on what kind of probability measure or sample space we are taking, as long as we have the exact characterization of the CDF of X. So this will not be a unique probability measure. That is true because there can be many random variables with the same CDF. So you can have a same sample space and you can define two different random variables which has same CDF, or you can have different sample spaces also. So these kind of things exist.